Um, okay, so as Simon mentioned, today I'm mainly talking about graph visualization, which I have been working on for quite a few years, and I was really excited about the topic because that was a few years back. There's a lot of work on and say networks. There's idea pop up like say scale-free network, which was published in Nature. So it's like a very big thing for computer science, and then also I think yesterday when Vicky Lamore talked about financial crisis or systemic risks, they also mentioned that okay, modeling is networks and do visualization as well. So this talk itself actually will be a little bit changed from what you have heard so far today. So far it's more algorithmic text analysis, but this is more focused on the visualization, and it's relatively lighter on the analytics part. So I first want to say I'm using graphs here as a term. These are not graphs. People might relate it to these. I will refer to these two as charts in my talks, and this is what I meant by graphs. And people sometimes also say these are networks, but usually in the mathematical sense, people will refer to these as graphs. So I'm mainly talk about things on the right. And so I'll talk about, so this is a general overview of graph visualization, and there's many related fields. So you can think of this as like a vertical slice in the broad field of visual analytics. It covers a wide spectrum from very applied to very theoretical. So it covers perception, psychology, vision, human-computer interaction, visual analytics somewhere in the middle, graph joint, this is a subfield. People are much more interested in the algorithm side, and there's pure algorithm as mathematics. So there's like a small group within a mathematics conference. People will talk about algorithm related to graph visualization. And so this is continues this arc of different application domain as well. So I worked on with visualization for sociology, biology, not so much on physics, but these are common fields where these are applied. And in this talk, so I'll be picking up either side. So I'll mainly talk about maybe the top half of the spectrum. So about say a little bit how people understand the graph by looking at the visualization, a different design of different visualization you can use, and much less so in terms of algorithm, how do you produce the visualization in the first place. So I try to cover the basics and assume you know nothing about graphs. Say for example, I assume you never heard of tree map before and didn't know how it works, but because I think it's quite an important concept. Some people might know it, but it's important for others who didn't know it. And I'll talk about visual presentation. So how do you design a picture of your networks or graphs, and layout algorithm. And so I'm not going to any details at all, just a general ideas how the graph is generated, the visualization. Some evaluation, how people look at the graph and understand it, whether it works or not, and how that's implication on how to design the visualization in the first place, and some applications on libraries. So I assume most of you would be interested in develop some visualizations of networks or the data you have. And sometimes you don't want to write any code at all. So I heard Giphy mentioned a few times, sometimes you can write a little bit of code, maybe JavaScript, or maybe a little more advanced into Java. So I talk about common things you can use to do these. And there's lots of things. Basically, only we touched on these topics. There's lots of things. I didn't go into depth at all. So, okay, I want to introduce two concepts again first, and trees and hierarchies. And so this, again, it's not the tree we're talking about. And so it's a simplified graph. So something looks like this. It also has okay, so we have to talk about first parent, child, and siblings. So oddly, this tree has a root on the top. And so if you can see root, the node called root is the parent of node 2, 3, 4. And in the same sense, 2, 3, 4 are the children of the root. And 2, 3, 4 themselves are siblings because they share the same parent, to some terms. And then we have the root. The root and leaf concept is exactly the same as a normal tree, but the root is the one on the top, and the leaf is the one which doesn't have any more children. So in this case, say node 5, 10, and all these nodes don't have further children. These are called leaves. Okay, and the hierarchy is very similar. And okay, that's a formal definition. But if you look at another example, this is called hierarchy. The only difference is a node, for example, node number 7 here, can have more than one parent. So 3 is 7's parents, but also 4 is also the parents. That's the only definition. The difference. And the reason I introduced this first is it's actually very important in visualization, and because they are, first, it's very common. In the real world, you get lots of data. I think an organization chart is a very common example of trees, and it's actually much simpler than general graphs, and which allows something you can, so okay, you actually can apply algorithms which apply relatively larger data size. And okay, so what is most famous? Tree visualization. The formal name called indented layout, but this is actually a tree visualization. And so this is showing the file structure hierarchy on your computer in a visualization way. And so that's called indented layout. It places all the items vertically, and the indentation shows the parent-child relationship. So okay, further to the left level, and that means the parent, and all these are the children of these parents. Windows Explorer, and it's actually showing part of the tree already only, and you can, it's very rarely expand all the directories on your file on your hard drive in Explorer, and it has a fairly bad aspiration. So when this part works fairly well in the Windows Explorer, and very rarely people have a monitor with very, say, this kind of aspect ratio, especially if you expand everything. So you wouldn't be able to use all the screen space if you only want to see the hierarchy of your file structure. Okay, and the second one. So I'm going through a few different ways you can represent and hierarchy or trees here, and we'll show some comparison later on. And so, okay, you can visualize trees in a form that's closely resemble to the natural trees. So we have a data structure here, you can visualize in this way. And okay, so in this way you actually put the root at the bottom, and each of these intermediate rows is shown as the branches. So it's fairly small, but you can see that's B3 here, which is represented by this fairly thick branch here. And you have D10, which is this one here. Okay, talk about these, and this is a 3D version, so make it even closer to what the real tree is like. And this is showing the Unix home directory. Okay, layered layout, and this is again another fairly common one and quite widely used. So this is similar to the example we see at a few slides back, and this is probably the most common way you see a tree visualized. And it's called layered layout because all these nodes are put on, say, parallel layers. And there's a different way you can actually put the root in the middle and use the concentric circles to indicate the layering and similar ideas. But most people seem to have a preference of this one, kind of because symmetry, but also to utilize the space better. So this is kind of give you a square-shaped space, which is much closer to use a normal display aspect ratio. Okay, dendrogram, and again, layered layout, and instead of, say, doing the layout, drawing or visualize the graph from the very top, it's from the very bottom, and it makes sure just all the leaf nodes, if you still remember, on all the very bottom level, at the same level, and it goes up. And in this specific case, it uses actually orthogonal edges. So it's focused on the leaf nodes. And actually, this particular example or this type of visualization is very common or popular in bioinformatics, where people do lots of hierarchical clustering and by grouping nodes recursively, and which lends naturally to this type of structure, visual structure. Okay, and a common example is phylogenetic trees, or example of that is called tree of life, where you can show the evolution of different species over time, and it can be presented in this way fairly nicely. Okay, and now I'm coming to tree map, and which I called space filling methods. So this is a type of visualization really designed to use all the space you can have on a display. And I have a fairly simple hierarchical structure or tree structure here, and this is what the tree map representation of that particular structure. So okay, you have to really look at, say, you have the root, which is the biggest square, or the rectangle outside. It has two children, node number 2 and node number 3. Number 3 has no further children, but node 2 does. So node 2 has further divided into 4 and 5, these two, and 4 is further divided, etc., etc. Okay, and so the containment is used to show the hierarchy, and the space is partitioned recursively to show, and so how big a node is depends on how many children it has inside. So it's okay. So it's much more space efficient compared to loading diagrams. So you can make that whole tree occupy all of this place because you can always change the aspect ratio, and to make sure it takes up all this display space. And I think it's quite effective in showing the leaf nodes if you just look at this visualization, not this one at all. But it's relatively difficult to understand the relationship between the nodes. Okay, and I think we've seen this picture somewhere already. So it was included, I think I mentioned included in Tableau now. And this is, but this is not from Tableau. This is some people done a few years back, and using tree map metaphor to visualize stock bucket, and the color indicates whether stock is increasing or decreasing, and these blocks represent different segments of the stock market, whether it's say oil or transport or something, or pharmacy, pharmaceutical, etc. Okay, and this probably will be the last one, and a different visual way to represent and hierarchies is called information slides. And this is again the same tree structure we had before, and this is actually how you present it. And so the root in the middle, and the two other blocks, or say wedges next to it, is node number 2 and 3 because these are its children's. And node number 3 doesn't have any further children, it's a leaf, so no more, to the outside circle. And node 2 has two nodes called 4 and 5, so you have 4 right next to 2 and 5 next to 2. So that's how you show the hierarchical relationship. Okay, so it's a radial version, and again the node size is proportional to how many children you have inside. And so this is like an advanced version of information slides. And for example, this is information slides in the middle, but what they do is actually they also include focus plus context techniques. For example, this part is difficult to see what's the details there, and you can select it, and the details will be expanded or zoomed out and displayed outside. So this part is enlarged part of this part. And you can do similar things. You can have a big information slides with some space in the middle, and you can select a small section and display it in the middle there. Which is a fairly neat idea, I think. Okay, so I covered maybe 4 or 5 different ways to show graphs, to show trees or hierarchies, and there's an evaluation in terms of how effective people use these visualizations to perform certain tasks. Usually you look at the data, you want to find something, and these are your tasks. And in many cases, not necessarily the most fancy visualization give you best performance in terms of accuracy or speed. So this is one of the visualization, and so it was done in 2004, and it compared the 6 different visualization systems. And we see this version of tree map, and this is a variation of tree map. It uses a little bit 3D shape for each blocks to show the hierarchy better. And this is something called beam tree. And this is similar to the radial visualization we see before, but it's actually combined with a little bit of distortion. And this is natural tree. And finally, quite difficult to see here, but this is the Windows Explorer. And a little bit detail on what's done using an eBay taxonomy. So this is, for example, if you use eBay, you can go to say maybe, I don't know, electronics or appliance first, and then go to say cameras and the digital SRR. That's their taxonomy. 5 levels with 5,800 nodes. So it's a quite shallow and wide hierarchy, and they do different tasks. 15 different tasks, and boast about tree structure and node attributes. Okay, and measured accuracy, completion, and user satisfaction. And so these top 2 is fairly common, and actually these all 3 are quite common. So you usually ask people about how much do they like the visualization afterwards. Okay, and the results, and Windows Explorer scores best. So this one actually scores best, both in terms of accuracy, completion, and user satisfaction. And only 3 maps achieve similar levels as Explorer. Others performs worse. So these 2 performs closer to this one, but these are not. Okay, so to me, I mean, it's a quite surprising results. And so basically they're saying, and all the people doing research spend all these years to come up with different ways. It's actually not any better than, say, the one people have used for decades.
Could you talk a little bit more about the 15 tasks that you do?
Okay. And I don't really have the list of these here, but and so if you're interested, actually, I'll send you a reference afterwards of this paper. And it's published. It's fairly easy to find it, actually. Yeah. Okay, and so there's 2 things I can see from the study, from reading the paper, how they do the experiment. So first, because most people are very familiar with Internet Explorer, and Windows Explorer, so know exactly how to use. They take time to learn to use how to use these, and also you have to implement a system to perform the tasks you require to do, but the functionality is not equal set. So for example, you might be able to do some tasks. There's some function here helping to do things better than the other things. Excuse me. Okay, so I think there's 2 things might be useful to look at the results of this study. So first, every conclusion from a study is constrained by the setup of the experiment. Do not generalize it a little bit too much. Say, people might tend to be so Windows Explorer is the best and tree visualization. But if you say more accurately, and Windows Explorer is best for these tasks on this specific data set and in these specific settings, so it might not be generalizable. And also the other things is actually very important is when you try to design a new visualization, you might want to think of, okay, not just to say make it perform the best, but also consider how that makes it easiest for the user to start using it. Say if you design one new visualization method which is based on this metaphor, even it might not achieve, say, better aspect ratios and all of these, or not look as fancy, but it actually may perform the best in the real world with people not, say, visualization researchers. Okay, and I have another study with comparison different representation. This time it's look at aesthetics. So this is only look at how people think how much do they like the visual presentation, not performing any tasks. So basically, you show them all these different representation, all use actually the same data. So we're seeing tree map. This is slightly different one we didn't cover. We show the layered ones. This is the Windows Explorer, and a few other fancy ones. The last one is the information slide or some best. And just ask them to rank them, which one do you think is the most beautiful or like the most. And anyone want to take a guess?
Sunburst.
Okay, someone likes Sunburst. Or, okay, anyone, which one you don't like most? Or ugly, the ugliest? Okay, this one is ranked the least aesthetically pleasing, followed by these ones. So these are less popular, and Interestingly, tree map is there, and also sunburst is ranked as most aesthetics pleasing. And so it's actually it's not so common people doing this type of evaluation. Most people test the utility of visualization to show, okay, my method lead to faster performance or faster speeds or more accurate. But actually, when I talk to industry people, and aesthetics appealingness is actually very important. So if you build some commercial product, doesn't matter how good that is, the first thing is people want to try. So if something looks ugly, people don't even want to bother, there's very little chance of the success. And if it's actually, so I think that's why, so in previous talks, you see all these fancy products, which are using, say, pie charts or 3D, all these shadings. The thing is just get people to use it first, and then maybe it actually doesn't perform that well. I think that's also something we should, and okay, so from my background as an academic researcher doing research in visualization, actually appealingness is actually maybe equally important as how effective the method is. If you want a method to be actually applied, adopted by many people, maybe the first step is actually get people interested in to try out your method first. Okay, and if you're interested, I can provide the reference as well. This is a 2007 Kai paper. Okay, so I'm going to talk about a little bit about layout, which is the method, how do you place the nodes to generate a visualization. So basically, in terms of any graphs, either tree or hierarchy or general graph, the data you have is just nodes and the connection between them. And a very important step in the visualization is to find the proper position of your nodes, so make the network looks better or graph looks better. So you already see the question there. And if you still haven't figured out, all these four are exactly the same graphs. It's just using different layout. So if you haven't really tried the layout before, you can see how much kind of impact the layout can have on your understanding of the graph. This will give you impression this is a circle, this should be a hierarchy, this is some kind of structure, but you probably, at a glance, you wouldn't think these are the same or similar to this one. Okay, the studies to show what makes a good layout. And so these are some things people try to optimize in their methods to produce a good layout. So in general, people agree edge crossings is something should avoid to improve the layout. So this one is better than this one, even though the same graph, because this one doesn't have crossing. Aspect ratio, most people would more like a square, closer square-shaped aspect ratio compared to very long and thin visualization. Edge length, and usually you prefer and shorter edge length, and with the assumption that, for example, if you need to find the path within the graph, it's easier to follow if the length is shorter. And something called angular resolution as well. Say, for example, in this visualization, you got lots of angles between edges which are really small, and in general, people think that's not a good thing. You want to maximize these minimal angles to improve angular resolution. And last one I listed is symmetry. So if there's a symmetry in your network, it's good to show, and it's actually usually quite pleasing to the eyes as well. Okay, so the study to try to find out which aesthetics criteria listed is most important. And so it tried to provide an order between these different aesthetics criteria. And in this study, look at 5 and edge crossings, edge bends. So in some cases, you can actually draw an edge, not necessarily just a straight line. You can have a polyline, so it can have bends. And symmetry, we mentioned, and angle, so angular resolution, and orthogonality. So actually, it's possible to draw your edges only vertical or horizontal, which I will show some example later. So this is what they used in the study. And so these are the pair, and they showed people these are exactly the same. All the nodes at the exact same position. The only difference is the bends. So all the edges are straight, but here some of the straight has a bend. And this is again a pair used for comparison. this one has less crossings, this one has more crossings. And okay, this is for the angle, and here the angles between the edges are relatively larger than the angles between the edges here. And this is what meant by the orthogonality. So you start to have edges which are either horizontal or vertical only, and this doesn't have orthogonality. And this is meant to be symmetry, but how difficult to see. Okay, this one is meant to be has more symmetry than this one. So okay, so basically based on performance of user doing tasks on a pair of graphs, and then rank how much difference in terms of performance they have. So it turned out edge crossing is the most important part, or most important aesthetics criteria for the people performing tasks on graphs. And there's less extent in terms of edge bands or symmetry. So these doesn't really affect people's performance using graphs that much, but does have some effects. And angular resolution and orthogonality doesn't really have impact on the performance. So people look at this one and this one. If they need to do some task, maybe find the path between a pair of nodes, and there's no significant difference using these two. Okay, next one is we're going to talk about a very common method called force directed methods to generate a layout for a graph. And the idea is you treat every node as a charged particle, or charged nodes, and all the nodes have the same charge, so they repel each other. And as a result, the nodes will not stay next to each other. Okay, so you have a small graph here, and each node has a charge, so repel each other, and that's what these lines are. So it doesn't really matter whether it's edge or not. Each pair of nodes has a repulsion force between them. And you have the edges then. So the edges are modeled as a spring. So each spring has a natural length. So it will give a pair of nodes an attraction force when the spring is stretched, so longer than the natural length. And if it's a repulsion force, and if it's shorter, it's basically if it's squeezed. And so each of these edges here is replaced as a spring, and each of the spring has an initial length. And for example, in this example, say for example, and because of the repulsion force between these two nodes, this spring will be stretched, and it will add an attraction force between these two nodes to stop them being too further away from each other. And in some cases, for example, maybe this one, maybe squeeze, and it will be shorter, and in that case, it will provide a repulsion force between these nodes to stop them to get too close. And as a result, this graph will be probably laid out as this, looks like this at the end. And anyone want to guess what the algorithm actually tried to optimize? Yeah, but if you look at if you think of the criteria we listed in the last slides, was that to optimize reduce number of edge crossings, or is reduce edge lengths, or improve angular resolution? Yeah, so actually it's best actually showing symmetry in the data. It's not necessarily that's actually so you can see fairly clearly any symmetry in these results. Okay, I'll show you an example. So this is a network layout. This is a network, and I try to lay out using force directed methods. Okay. Okay, so I'll do it again so you can see it clearly. So you can see the nodes start moving around because of force, and the movement start to gradually reduce, and eventually it will stop.
It is D3.
Yeah, this is D3. Yeah. And so there's a, sorry? Okay, so I have to, it's changed fairly quickly. So this originally is random, almost random placed. So you probably see this type of visualization online somewhere already. And one of the reasons is actually the idea is fairly simple to implement, say the force between different nodes. And the animation, lots of people find it quite interesting to see the nodes bouncing around, etc.
Does it always fall the same way?
No, it's not deterministic. It's not necessarily always the same way. So has a few effects. Usually, if you every time it's always start at the same position, starting position for every node, it's more likely to fall into the exact final nodes. Okay, keep that. Okay, next I'm going to very briefly talk about the director graph and the layered layout. So we already came across the layered layout before. So basically put nodes onto different horizontal layers. And in this case, it's a general graph, not a hierarchy or tree. And this is actually a very difficult problem. And it's very slow, even with heuristics on large graphs. And large here really just means hundreds of nodes. It's already quite slow. And definitely it's not optimized. These are just approximation algorithms. And the common framework of doing this is called the Sukiyama methods. First, I try to put nodes into layers. And this is only decide which layer they will be, so not the order. And you move nodes within each layer around to reduce the crossings between two layers. And this is actually the final, that's what that looks like. And finally, you find horizontal positions for each of nodes. So the second step, the first step decides, okay, this node's in this layer, this node's in this layer. Okay, the second step decides ordering between nodes within each layer. And the final step actually decides exact position of each node within the layer. For example, they have to leave a gap for this long edge to go through. So that's done in this last step. So it looks actually quite easy, but actually each of these steps are very difficult. And for example, if you want to minimize the crossing between two layers in the second step, it's an NP hard problem already, even though there's fairly simple heuristics to do that. We're reasonably good. Okay, I'm showing an example. So it's quite difficult to demonstrate step by step. So I'm just showing what it looks like when it's laid out. So what I'm showing you here is a graph with random positioned nodes, but it is a directed graph. And I opened it in something called Y graph editor. If I come on. Okay, so that's probably as big as it can get. And so I'll talk about these tools a little bit later on as well. But say I choose a hierarchical layout. You've got lots of different parameters. And I choose a typical one. And this is how it's done. Essentially, it's doing all these 3 steps in one go. And this is what you want the final results with. And you can quite easily see this is what it looks like using a force director layout, which we just covered. And there's many other layouts you can try out here as well. Saying this is a circular one, and this would be an orthogonal, where all the edges are either vertical or straight. Okay. Okay, so there's again studies to show, okay, does this layout actually helps? And this study compared quite a few different layouts. So force direct, which one we covered, 3 variations of those. This is the orthogonal, which is C. All the edges are either horizontal or vertical, and there's planar. And that's something a little bit tricky we didn't cover. But planar basically means you can draw a graph without any crossings. and not all graph is possible to do that, but it's something we can do. And the results is one method performed significantly worse, which is this one, which basically is a planar grid drawing, and for the rest, even the layout is quite different for a task given in a study, and the performance is more or less the same. There's no significant difference. And finally, I'm going to talk about a big problem facing people doing graph visualization is large or sometimes just dense graphs. I show you an example here. This is not particularly large graph. I would say maybe 30 nodes about, but it is really dense in terms of got lots of edges. And here, all the edges are drawn with transparency, so it's actually not too bad. But if you all draw solid lines, you get the typical, say, the hellball problems, which you see already. I think today's talk, in Chris' talk, he showed this small network on the Twitter about Scala, but it's already can't see anything really. So some people try to using connectivity matrix to show the network, and so it's different way to represent, and each row is a node. Each row is a node in the graph, and each column again is the same, also a node in the graph. And if there's dot there, that means there's edge between these two nodes. And the good thing is you will never have edge crossings in matrix representation. And disadvantage is if you have a graph which is not as dense as this one, most of the case it's not, and you have lots of empty space in the matrix. And in this specific example, it works quite well because this is a very, very dense graph. Okay, so people do evaluation to compare these two types of visualization. And for small graphs, they find node link diagrams, which is this type of representation, are always better. And when they say small, they say about 20 nodes or below. And we have more than 20 nodes, matrix are better, except for path finding. So, for example, here, this is better for all kinds of tasks. You can, except for path finding, is to find the path between two nodes. And for example, you can imagine if you want to have a node here, and you need to find a path linked to the other nodes here. And it's quite difficult here in the matrix representation. And so this is something, a mix of the two representation called a matrix. And so part of the graph is represented as a matrix, for example here, but they still keep edges to the less well-connected part of the graph, so you still have edges there to show connected to the other nodes. And this is a paper in 2007 or 8, and showing the people in the InfoVis domain how they are connected. Okay, and the other techniques quite popular recently is to using curved edges in graphs to visualize the network. And so this is actually produced in Giphy, but it's actually your LinkedIn network. And so I'm not sure if you're aware of this, like I say, LinkedIn actually put a lot of support behind the development of Giphy. And if you go to their lab, I think called InLabs at linkedin.com or something, you can log in and it will produce a visualization of your professional network. And this is mine, and this is your class set, and actually visualize using the curved edges. And I would say, if you can imagine, if all these edges are straight lines, it will look a lot more messier than this. And recently there's a method called edge bundling and confluent join. It's something looks like this. And so you have all the nodes on the side, and these are edges in between them. And you can bundle edges, which say goes from the same region to the other similar region. You can bundle them together, much more easier to show overall structure. So I did evaluation and to look at how people perform using curved edges. So these are 3 different types of curved edges I compared to the study, and again compared to a graph with just straight edges. And the result is, and in terms of aesthetics, and people still prefer straight lines. And in terms of performance, the straight line is the best, and this one has a similar performance as a straight line. And so again, so that's just a study. And if you want to look at the details, I can provide you the reference. Okay, and finally we talk about some of the software you can use to do the visualization. And the first thing is called YAD, which is the software I just showed. This one here. And so that's the interface, similar to what we just saw. And it's a commercial product, but the editor itself is free. You can download or use it. And it's including many layouts and network algorithms. So the layout is what we just saw. A few examples, network including different centralities, which I didn't talk about, and including, say, the community or clustering coefficient calculation, which Chris mentioned in his talk. These are all implemented, and it's quite easy to map these results to different visual attributes. I think here I did a very simple centrality analysis and mapped the values to the size of the nodes. It's very mature. It has been around for a long time. So these are developed by people who are experts in graph drawing algorithms. They commercialize the results and make it a commercial package. Okay, so there's Office Giphy, and it's mentioned a few times, and it's an open source software for mainly, again, for social network analysis, and it's still in development, and so actually progress fairly slowly. And so it is okay if you want to just use this as a software, but I personally try to write some plugins. For example, adding a new layout plugin for Giphy. I find it relatively complex, not so easy to get on started with. But I would say YAD is relatively much less well known, but in terms of implementation of layout, and YAD is definitely better, and it can do all different type of social network analysis here as well. So it might be worthwhile to try it out if you haven't. Okay, so I'll talk about some libraries. So these are the things which you want to write some code yourself, but you don't want to implement the layout yourself. So there's JGraph. It was a commercial software, but obviously it was not doing as well as YAD, so they made it open source. It has probably the best free implementation of different layout algorithms, because again, there's a group of experts who are experts in graph drawing algorithms. They have both Java library and JavaScript library. And there's GraphViz, and this is a research group and at AT&T Research Labs, and they are experts in layered joins. And it's particularly good doing at hierarchical layout, but of course it also has simple force direct and radial and circular layout as well. And this is in C, so basically these are in Java and these are C, so it depends on your language. And Yung again is a library, again in Java, as in the name, and focused on the social network analysis. And there's also a layout implementing different visualization libraries. And someone already mentioned D3, which is actually we currently try to use. And the force direct example you saw there was using D3. And it's got lots of other nice implementation of different visualization as well. And ProtoViz, these are all JavaScript based information visualization library, including some layout. And there's Flare, which is Flash based, Prefuse, which is Java based. And I just want to say, all these, except this middle one, are developed by the same group, actually same person. And this is like the first version, this is second version, third version, and this is the latest version. So if you're going to pick one, I would recommend you go try these three. So it's JavaScript based. The good thing is it already has lots of different visualization implemented there, and you can just use them in your code. Okay, and there's also a domain-specific one. Someone might have heard of Cytoscape, and it's very much designed for biologists, and usually using people doing genomics or protein interaction, those kind of things. Okay, and also there's Payark. and which is designed specifically for social network analysis and for being around for a long time. And the good thing about Pike is, again, it's run quite fast. The people developing this is really expert in algorithms, so it runs relatively fast for large social networks. And in terms of computation, say if you want to compute between centrality and a big graph, maybe this will be a good choice. But then if you do visualization afterwards, maybe you want to just export the data and do visualization somewhere else. Okay, and this is my last slide. So I touched on different visual representation, how you can show a graphs, and more specifically trees, and layout algorithms. Two types of layout algorithms for general graphs. One is using a force model, the other one is layered. And lots of evaluations, because I think it's really important to see how well these different methods work in reality, and some software and libraries you might be able to use if you want to do some visualization yourself. And didn't cover a lot. And finally, I just want to mention one reference, and this is a fairly recent review on graph visualization, including visual representation and methods. And I think the slides will be available, and if you want to find out more about research in the graph visualization area, I think this will be a good place to start. Okay, that's all.